Hello, and today we'll be doing chapter 23 to 24 as homework. Question number 6. Starting with part A, two plates of a parallel plate capacitor have an area of 0.46 meters square and are 3 millimeters apart and initially have a vacuum between them. A power supply is attached to the capacitor, charging it to 4 kilovolts, and is then disconnected. Dielectric sheet is then inserted that fills the space between the plates, and the potential difference between the plates is decreased to 2.5 kilovolts, and then the charge on each plate remains constant. Find the original capacitance. So to find the original capacitance, we can get that by using the capacitance formula, which is like the vacuum times the area divided by the distance. And so for this one, you can use the capacitance is equal to 8.85 times 10 to the power negative 12 farads per meter times 0.46 meters squared divided by 3 times 10 to the power of negative 3 meters, because that times that millimeters. Okay, so 0.46 divided by 3 times 10 to the power of negative 3. And so we get 1.53 times 10 to the power of 2, which is going to multiply by 8.85 times 10 to the power of negative 12. And so we then get a capacitance of 1.4 times 10 to the power of negative 9 farads. Oh, 1.36. You can round them. And so the next part says to find the charge of the capacitor plate. So the charge is just literally the charge is equal to the capacitance times the voltage. So the capacitance we just calculated, we can do 1.36 times the voltage 4 that was shown earlier. And so, yeah, 4 kilovolts. So I can write this as our charge is equal to our capacitance times our voltage. Then write this as charge is going to equal 1.30, let's just do 36 because it said that on there. 10 to the power of negative 9 farads times, what is it, 4 kilovolts. So that's 4 times 10 to the power of 3 volts. So 0.36. So this is 0 in front of it. 1.36 times 10 to the power of negative 9 times 4 times 10 to the power of 3. So then we get a charge of 5.4 times 10 to the power of negative 6 coulombs. The next part is asks us to find the dielectric constant of the dielectric. And so to find the dielectric constant, you can just use the voltage formula, which is the voltage equal to the initial voltage divided by the dielectric constant, which we can rearrange to get the dielectric constant times the equal to the initial voltage divided by the voltage. So write this down. Oops, wrong button. And so scroll. Voltage is going to equal the voltage of initial divided by dielectric constant, which you write equal to our dielectric constant equal to our initial voltage divided by our new voltage. And so it writes down this times that. Wait, let me scroll up. Kilovolt, yeah. So 4, another one. And so our dielectric constant is going to equal 4 times 10 to the power of 3 volts divided by 2.5 times 10 to the power of 3 volts. And so 4 times 10 to the power of 3 divided by 2.5 times 10 to the power of 3. So that's going to equal a dielectric constant of 1.6. Is it 2.5, right? Yeah. And so it now is asking us to calculate the new capacitance after you insert the dielectric constant. And so basically what we're just going to be doing is multiplying the capacitance, our initial capacitance times our dielectric constant. And so that'd be the 1.36 up here times our dielectric constant right here, 1.6. So you can write this out, the formula. So our capacitance is going to equal our dielectric constant times our original capacitance. So 1.6 times 1.36 times 10 to the power of negative 9 farads 0.36 times 10 to the power of negative 9. And so we're left with our new capacitance of 2.18 times 10 to the power of negative 9 farads. That's right. Well, it rounded down, so 2.17, but that's fine. So the next one is just going to ask us what is the magnitude of the induced charge in the faces of the dielectric sheet. And so basically to get that, you just need to use the Q induced formula, which is the charge induced, which is equal to the charge times 1 minus 1 over the dielectric constant. So in like our case, it would be 5.4, and then times 1 minus 1 over 1.6. And so let's put this out. Let's write this. Our charge induced is equal to our charge times 1 minus 1 over the dielectric constant. And so let me write this over here. 5.4 times 10 to the power of negative 6 coulombs times 1 minus 1 over 1.6. Oops. 1 minus 1 divided by 1.6. 0.375 times 8.8. Oh, sorry, wrong thing. 5.4 times 10 to the power of negative 6. Oops, double fives. And so then we get a charge induced of 203 times 10 to the power of negative 6. And this will be in coulombs. So, sorry, the two sheets of a parallel plate capacitor each have an area of 1.2 millimeters square and are 4.5 millimeters apart and initially have a vacuum between them. You connect the power supply to the capacitor charged at 3.5 kilovolts, and keeping the power supply connected, you insert a sheet of a dielectric constant of 2.5 that fills the space between the plates, and find the original capacitance. So basically, to do this, you just need to use the same formula we had earlier. So the capacitance is to do the vacuum times the area divided by the distance, and so you have 1.2 meters squared divided by 4.5, and then times the 8.85. So write this out. So erase this first. So our capacitance is going to equal our vacuum times area divided by distance. And so write this over capacitance is times 8.85, 10 to the power of negative 12 farads per meter, times 1.2 meters squared divided by 4.5 times 10 to the power of negative 3 meters because it was in millimeters. So 1.2 divided by, oops, that's the wrong one, 4.5, 10 to the power of negative 3, 2.6 times 10 to the power of 2, times 8.85 times 10 to the power of negative 12. And so then we get a capacitance of 2.36 times 10 to the power of negative 9 farads. So part G, calculate the original charge of the capacitor plates. It's basically the same formula you used earlier. Is just the charge is equal to the capacitance times the voltage. So that'll be the 2.36 that we have, and then the 3.5 microvolts or kilovolts, which is 3.5 volts times like 10 to the power of 3. So yeah, our charge is going to equal capacitance times voltage. This charge is going to equal 2.36 times 10 to the power of 9 farads times 3.5 times 10 to the power of 3 volts. Let's write this out. 2.36 10 to the power of negative 9 times 3.5 times 10 to the power of 3. And so our new charge is going to be 8.26 times 10 to the power of negative 6 coulombs. And so this one's going to ask us to find the capacitance once you insert the dielectric. And so to do that, you just do the 2.36 times the 2.5. And so I want our capacitance for that. So our new capacitance is going to equal our dielectric constant times our original capacitance. And so Cn 2.5 times our 2.36 times 10 to the power of negative 9 farads times 2.36 times 10 to the power of negative 9. And so we get a new capacitance of 5.9 times 10 to the power of negative 9 farads. And so now it says to calculate the new charge on the capacitor plates. And to just do that, you just do the same charge and everything we had, was just the 5.9 times the voltage that we have, so 3.5. And write this up. Charge is going to equal our capacitance times our voltage. Right, your charge is going to equal to 5.9 times 10 to the power of negative 9 farads times 3.5 times 10 to the power of, what is it, 3 volts. And so then we have a charge of 2.07 times 10 to the power of negative 5 coulombs. So the next answer is asks us to calculate the magnitude of the induced charge on the faces of the dielectric sheet, which is just the same Q induced formula we had. So we have the Q induced, the charge is equal to the initial charge times 1 minus 1 over the dielectric constant. And so to be out, so our induced charge equal to our initial charge times 1 minus 1 over our dielectric constant. And so then we can write this as our induced charge is equal to 8.26 times 10 to the power of negative 6 times 1 over, well, times 1 minus 1 over 2.5. So it's 1 minus 1, 1 minus 1 divided by 2.5, 0.6 times 8.26 times 10 to the power of negative 6. So our new Q induced is going to be 4.96 times 10 to the power of negative 6 coulombs. So now part K, with a vacuum between its plates and a parallel capacitor has a capacitance of 4.5 microfarads, and you attach a power supply to the capacitor, turn it at 3.2 kilovolts, and then disconnect it. You then insert a dielectric sheet that fills the space between the plates. The potential difference between the plates decreases to 1.2 kilovolts, and then the charge on each plate remains constant. Find the energy stored in the capacitor before you inserted the sheet. So to do that, you just basically use the potential energy formula that we had, which was let's see, potential energy. So our potential energy formula is going to be our, well, not potential energy, our stored energy formula. So our is going to equal to a 1/2 times our capacitance times our voltage squared. And so since we have that, we have our stored energy is equal to 1/2 times, what is it, 4.5. So 10 to the 5 that times that, so 10 to the power 6 farads. And then we have our voltage, which was 3.2 times 10 to the power of 3 volts squared. So it's just 3200. So let's do that part first. 3.2 times 10 to the power of 3 squared. So 1.02 times 10 to the power of 7. So let's do that 10 times, well, times 4.5 times 10 to the power of negative 6. And we can divide this by 2. And so then we get a stored energy of 2304 joules. That's correct. So then it asks us to find the energy stored in the capacitor after you insert into the sheet. And so we can do this by using our formula for the dielectric constant that we have, which was the original. Let's see, so we have the charge times our capacitance times our voltage, and then we have our original capacitance formula, which we can have as the dielectric constant times our constant, our capacitance, and then we can substitute our formulas in there, and so we can write this out as the dielectric constant times our capacitance times the voltage, and then we can equal that to our capacitance times our voltage, and then rearrange that. We left with our dielectric constant over our initial voltage divided by our final voltage. And so we can write this as dielectric constant is equal to 3 times 10 to the power of 3 volts, and then 1.3, 3.2, sorry. And then what's the other one? 1.3? 1.2. So 1.2 volts, kilovolts. So that's 1.2 to the 10 to the 3 volts. So 3.2 times 10 to the power of 3 divided by 1.2 times 10 to the power of 3. So we get a dielectric constant of 2 point, let's round this to 6.7. And then once we have that, we can then plug in our values and see we have the capacitance of 4.5. So then we can write this as, we can solve for our capacitance now and get it. So we can do our capacitance that we had earlier, which is the this one. Capacitance is equal to our dielectric constant times our initial capacitance. So 0.67, and then we can write this as 4.5 times 10 to the power of negative 6 farads. So 1.2 times 10 to the power of negative 5 farads. And now that we have that, we can find it after our capacitance stored energy. So we can use this formula. So stored energy is going to equal 1/2 times 1.2 times 10 to the power of negative 5 farads. And then we can write this also as our 1.2 times 10 to the power of 3 volts squared. 1.2 times 10 to the power of 5, negative 5, times 1.2 times 10 to the power of 3 squared, divided by 2. So then we're left with a stored energy of 8.64 joules. That's correct. So part M, if a vacuum between its plates is a parallel plate capacitor has a capacitance of 5.2 microfarads, and you attach a power supply to the capacitor charging at 1.5 kilovolts, keeping the power supply connected. You insert a dielectric sheet with a dielectric constant of 2.55 that fills the space between the plates. Find the energy stored in the capacitor before the sheet is inserted. So we can use the stored energy formula to solve this. So we can just do the 1/2 times the 5.2 microfarads times our voltage is 1.5 kilovolts. So let's erase this. We write this one. So our stored energy formula is going to equal to 1/2 times our capacitance times our voltage squared. So we can write this as stored energy is equal to 1/2 times our 5.2 micro. So that's 5.2 times 10 to the power of negative 6 farads times this 1.5. So let's write this 1500 volts squared. So let's do 1500 squared. Oops, sorry. 1500 squared times 5.2 times 10 to the power of negative 6 divided by 2. And so then we're left with a stored energy of 5.85 joules. And then the last question, part N, is this asking us to find energy stored in the capacitor after the sheet is inserted. So we can just use the we can solve for the capacitance and then plug it into the formula after. So our capacitance formula for that is going to be capacitance is going to equal to our dielectric constant times our initial capacitance. And so that would just be capacitance is equal to our 35 times 5.2 times 10 to the power negative 6 farads. 135 times 5.2 times 10 to the power negative 6. And so, let's see, oops, I typed it wrong. That's right, 2.35 times 5.2. Divided by 10. Okay, so we can have, let's rewrite this as this 12.22. So let's write this. I typed it wrong. I'm like 2.35 times 5.2 times 10 to the power of negative 6. 1.22, that's right, 1.22 times 10 to the power of negative 5 farads. And then we can write this times our thing. So our equation right here. And so our stored energy is going to be 1/2 times 1.22 times 10 to the power of negative 5 farads times, what is it, 1500 volts. Is it? Yeah, 1500 volts squared. 22. It's 1500 squared, and then we can do 2.25 times 10 to the power of 6 times 1.22 times 10 to the power of negative 5 divided by 2. And so then we're left with our stored energy of 13.73 joules. Um, 75. Like, okay, I just did that wrong. So let me see. .55. Wait, I just said 35. No wonder. So here, 2.55, not 35. So 2.55 times 5.2 times 10 to the power of negative 6. So this would be 1.32 times 10 to the power of negative 5. And then we can redo this one again too. So erase this. So you can write it out at the end. So 1500 squared, 2.25 times 10 to the power of 6 times 1.32 times 10 to the power of negative 5 divided by 2. And so we're left with, let's round this up, 15 joules. That's correct. Yes.